So make sure we've got a list of rules that encompass both the ionic and the covalence. We've got a list here on the left side of the page. We've already talked about how ionic compounds, it's kind of easy to figure out what they are. What gets kind of weird is what happens with the covalence. So I'm going to go through this list, and then we are going to figure out the charges of the elements on the right. So if you have a compound that contains an alkali metal, so that's going to be something in this column and going down, this column, it's going to get the charge that it would naturally want to have. It gets the most priority over everything. So for example, if we're looking at the NaCl, the Na gets to be +1 in both of these cases. And the other element adapts. So the other element, because the whole thing has to be neutral, because you can see there's no charge in the corner, this one has to be -1, and the fluorine has to be -1. Now, if you look where they are, you'd kind of be like, but that's what they would have been anyways. Right, and that's because these are ionic compounds. But we're kind of coming up with like a series of rules to consider everything. Let's look at the MgCl2, and notice there's no alkaline earth in there, but there is an alkali, but there is an alkaline earth in there. And so what we'll do with the alkaline earth is that we'll take this one and we'll make this +2 because that's the charge it wants to be. That's what it normally would want to be. It's got the strongest ability to do that. Then we'll make chlorine adapt. And so the whole thing again is neutral. So if we're trying to figure out this one, it's like saying 2x. So it's like saying 2x, I'm going to put the 2 on the side of the 2x. A lot of people like that way. I'm going to subtract the 2 from both sides. So I have 2x equals -2. So x equals -1. So what that means is that my chlorine, each of them have a value of -1. Again, when you look at that, you're probably like, but that's what chlorine would have had. It would have been -1 anyways. Why are we doing this? Okay, well, again, that's an ionic compound, and that's why it happens like that. So we are now moving into rules that will involve potentially covalent compounds. And you can see what happens there. Because in a covalent compound, one of the elements, even though they both are on this side, and they're going to want to both be negative, based on all of our charges up here, with oxidation numbers, one of them is forced to be positive. So we'll look at the OF2. So with the OF2, notice that we don't have alkali nor alkaline earth, but we do have a fluorine. That's the one that gets its preference. So that's -1, and there are 2 of them. And so we're going to try to figure out what x is. So if we come over here to do our math over here, x -2 equals, and it's all 0 because it was neutral. All of these are 0 compounds. They're all neutral. So I'm just going to add 2 to both sides, and I get x equals 2. So that's my value. It's +2. And again, now suddenly you're going to be thinking that's really weird because oxygen shouldn't go -2. Well, it does when we're talking about ionic things. Oxygen goes -2, it's going to grab the electrons. But when we're talking about oxidation numbers, they are a little bit different. And they have to do with the ability of the electron to move around in a reaction. We're not just talking about a bond within these 2 elements. And this concept of what the electrons are doing and why we care, we already talked about. You're going to see more of this in Gen Chem 2. So it's kind of like we're teasing out a little bit of information about it, and you're going to revisit it then. So you really only have to figure out oxidation numbers. And you have to understand oxidation reduction, which one is which, and that's it. So we're going to look at the HCl. So H, in this case, in the HCl, we don't have an alkali. We don't have that. We don't have that. So the hydrogen gets its preference, which means that the chlorine has to be -1. Again, that kind of makes sense. You're like, wait, but that's what it should be, right? So that compound tends to have, it has both covalent and ionic tendencies. This is an acid. Acids are kind of funny, but you're right that it does match exactly what you'd expect. But now look what happens when you have an alkali metal in there. So we stop right here. The alkali gets his preference +1. The whole thing has to be neutral, so that forces the H to be -1. And again, you're thinking, wait, but it should be +1. So this is the whole thing. Oxidation numbers are not the same thing as charges. It has to do with what's going on in the full reaction, not what's just going on right here, okay? So again, it's when you go to some weird kind of covalent, odd bonding situations, that's when they really become less what you expect. Finally, if you have something like NO, it doesn't have alkali, not alkaline earth, no fluorine, no hydrogen, then it's just based on electronegativity. So here's our N, here's our O. So the O is more electronegative. That's the guy that gets his charge. The nitrogen is going to have to be what's variable, or what we're figuring out. So we're going to add 2 to both sides, and that's going to give us X is equal to 2. So what that means is that our nitrogen here is plus 2. So I'm hoping you'd see that there's just a difference in some cases and there's not a difference in others, and try not to let it worry you too much. You just kind of want to follow the rules in order, and you'll get the oxidation number correct every single time.